Welcome to Saitechinfo channel, my dear students. In the previous class, we discussed about the surface chemistry part 1, where I was explaining the adsorption and catalysis. Now we need to go to other parts, that is colloids and emulsions. So before taking the colloids, let me explain about the last part of the catalysis that I have left due to want of time. Let me complete that one. That is the industrial significance of catalysis. That's very important. And after that, let me take up the colloids, the chemistry of colloids, followed by emulsions. Okay. Shall we enter into the topic? Are you ready? Right. Before that, I'd like to introduce this sketch note drawn by one of my students, Akash. He has done wonderfully. So you should also have this habit of taking down concept mapping or sketch notes. See, the entire topic is broadly divided into adsorption, catalysis, colloids, and emulsion. So here's illustrated beautifully all the points, almost whatever I have discussed in the previous class. So he has summed up everything here. Okay. So very good, Agash. So you should be able to recap everything in one page like a cheat sheet. So this is one of the best examples I would recommend to have such or to create such sketch note for each topic and subtopic. So such kind of concept maps and sketch notes will be very useful for you. So here's clearly explained about the adsorption. So where he has listed out all the subpoints, and also that is he has classified the adsorbent and adsorbate, the type of adsorption, then what are the applications of adsorption, then the famous Freundlich equation. So these are all covered in a single page. Okay, that's good. So similarly, the other student, Pavani and Gokul, they have also done it. Let me show that, and you can go through that for a while. And why don't you try to create such sketch notes? You can send it to our website so that we will be able to post it in our website. Okay. This is done by Pavani. So everyone has got his or her own what do you call it, creativity in developing the sketch note. Okay, so he has beautifully arranged all these points. The nodes are very clear. So when we consider this absorption, the adsorption and the absorption. So what are the differences between these two? Then what is adsorption? Then he has explained about the adsorbent and adsorbate also, and here she has explained about the physisorption and the chemisorption. So she has listed out the comparative studies. Then she has explained the adsorption of a gas by solids. Okay, so where more adsorption happens, and what about activation? So she has listed out all these points. She has not missed even a single point here. And then in the fourth node, she has given the adsorption isotherm, where she has beautifully illustrated the equation. Only thing missing is the graph, so that can be included. Then The same Freundlich equation can be applied for adsorption of liquid phase also, where concentration term is very important. So likewise, and she has listed out the applications here. Okay, you please watch this. So this adsorption sketch note or concept map has been done by Gokul. So he has illustrated his sketch note. He has tried to include everything and he has included the plots also very nicely. Okay, so that is P versus X by M. That is very, very important. And he has given the importance to the title Freundlich adsorption isotherm. Okay, so you should know what are important, what are not important. So you have to highlight the important titles. That's very important. Okay, good. And he has explained the adsorbent adsorbate physisorption versus chemisorption. So almost he has covered everything. Okay, very good, Gokul. Thank you. Now let us get into the topic. And before discussing the colloids, let me discuss about the industrial importance of catalysis. Industrial importance of catalysis. Here we can discuss the major three important processes. One is Haber's process. Second one is Oswald's process. Third is contact process. Contact process. In the Haber's process, ammonia is produced. In the Oswald's process, nitric acid is produced. In contact process, sulfuric acid is produced. Here, the reactants are nitrogen and hydrogen. Both of them are gas. These are reactants, this is product. And in this case, we take initially ammonia that is oxidized using oxygen. Then it is converted into nitrogen oxide. Okay, nitrogen monoxide, nitrogen and nitrogen dioxide, and followed by addition of water. And here the major reactants are sulfur dioxide, oxygen that is converted into sulfur trioxide. Then again it is added to water so that you are able to get sulfuric acid. And the catalyst involved in this case or catalyst is finely divided ion, and molybdenum acts as promoter. In this case, platinized asbestos act as catalyst. And here, platinized asbestos or specifically vanadium pentoxide, that is a better catalyst. And the reaction temperature is 723 to 773 Kelvin in the case of Haber's process. In Oswald's process, the temperature is 573 Kelvin. In case of contact process, it is 673 Kelvin to 723 Kelvin. Now let us discuss the reaction involved here. In this case, nitrogen as gas combines with hydrogen of 3 moles to give 2NH3. That is also gas. So we have already indicated the catalyst and reaction conditions. And in this case, first ammonia is taken, NH3, that combines with 5 moles of oxygen. Here 4 moles of ammonia. All are gases to give 4 moles of nitrogen oxide, NO, gas plus H2O, 6 moles of H2O. And there is a second stage where 2 moles of nitrogen oxide combines with oxygen to give 2 moles of nitrogen dioxide. Then this 4 moles of nitrogen dioxide that is combined with 2 moles of water, so that you are able to get 4 moles of, along with oxygen, then 4 moles of nitric acid. And as far as the contact process of manufacture of sulfuric acid, we already discussed. You can refer that previous video also, where the first step is formation of sulfur dioxide from sulfur trioxide from sulfur dioxide and oxygen. So sulfur trioxide. So 2 moles, 2 moles. And then sulfur trioxide is combined with H2SO4 to give oleum, H2S2O7. And from oleum, by diluting, we get sulfuric acid. So for a detailed video, you can refer the previous video or lecture. So these are the major industrial applications of catalyst. Okay. Solutions can be divided into 3. True solution, suspension, and we have in between colloidal dispersion, or you can simply put colloids. Among these three types of solution, true solution, where we already know it consists of two parts, solute and solvent. We can consider sodium chloride solution. So once sodium chloride, the solute is dissolved in substantial amount of solvent, you cannot see. It means it's invisible in solution. So if it is not visible, if the solute that is dissolved in solvent is not distinguishable, then we can call it homogeneous solution. That is why it's called true solution. Homogeneous. There is no physically distinct phase. But in the case of colloid, we have suspended particles. In this case, these suspended particles are visible in naked eyes. Whereas in colloids, being very, very small, the dispersed particles are very small. You cannot see that with the normal eye, but with the help of microscope, that is visible. It means its particle size will be 10 power minus 6 meter to 10 power minus 10 meter. Micron to almost angstrom. That is, most of the colloidal particles are in 10 power minus 9 meter also. That is called nanometer. And in the case of suspension, so we are not going to discuss about this aspect. Anyway, we'll be discussing in detail about this part, that is colloid. Okay. Now, our focus of attention is colloid. This colloid consists of two important parts. One is dispersed phase. Dispersed phase. The other one is dispersion medium. Dispersion medium. We used to say, in the case of true solution, solvent is the major part. Similarly, in this case, dispersion medium is the major part. Like solute, it occupies the smaller portion. The dispersed phase occupies the smaller portion, but uniformly spread. And the colloidal particles, that is the dispersed phase, its size is around 1 to 1000 nanometer as diameter. It means 10 power minus 9 meter to 10 power minus 6 meter, that is 1 micron. It has got some wide range. The speciality of colloidal particle is its enormous area. It has got wider surface area. So the colloidal particles, they have very large surface area. Let me explain about this. See, that is, let us have a square or a cube. Let us draw a cube, and this cube has the surface area 6a squared, total surface area. Let me say this is 2 centimeter. The side is 2 centimeter, that is A is 2 centimeter. So all sides are equal. Now what is the total surface area of this cube? That is 6a squared. Therefore 6 into 2 squared, that we know. So 24 square centimeter is the total surface area of this cube. Now let me divide this into 2 equally divided on all sides. So vertically I have cut, and vertically in this way I have cut, and horizontally I have cut like this. Now how many cubes I can get? Almost 8 cubes. Is it not? 8 cubes. So the surface area of each cube, how much I'll be able to get? Let me take one cube from this, a small cube cut from that, the small cube like this. Okay. Now let me check, because this will be 1 centimeter, 1 centimeter, height 1 centimeter. Let me check the TSA, total surface area. The same formula is applicable. So I can put 6 square centimeter. You may think that by reducing the size, the surface area has decreased. But it may be amazing fact when I say that it increases doubly. How? Because we have 8 cubes, So 8 into 6, how much? 48 square centimeter. Now do you agree with me? So by reducing the particle size to half, I am increasing the surface area double. Do you agree with me? So I have mathematically proved this. Okay? Just imagine, if it is the case, then how about the particle size? Suppose, say that is, I have some cube around, say 1 centimeter side. Okay, I have 1 centimeter side cube. So when I have this 1 centimeter size cube, okay, when I have this 1 centimeter size cube, and I am going to divide this, just imagine, I am going to divide this 1 centimeter cube. Okay, let me draw that. I have a cube like this, the same logic. Okay, now this has the side 1 centimeter. Please remember, this is 1 centimeter. Okay, now I am going to divide equally into 10 power 12 cubes. You just remember, I am going to get this equally divide and get 10 power 12 cubes. What about the square centimeter? That is the total surface area of this cube. 6 into a squared. 6 into 1 squared, that is 6 square centimeter. Now I have divided into 10 power 12 cubes. You just imagine. This results 60,000 square centimeter. Okay. You just imagine, if it is a 60,000 square centimeter, that means a 6 square meter, how large it is. It means finer the particle size, take down this very important thing. Greater will be the surface area. Do you understand this logic? Okay, note down somewhere. Finer the particle size, greater will be the surface area. And that is why, even that is when the surface area increases, there is a problem of wettability. So, by increasing the surface area, we will be struggling to properly process the materials, surface, I mean, that is such size of materials. So, in this case, the colloidal particles have enormous surface area per unit mass as a result of their small size. Do you understand this? Okay. So this enormous surface area that leads to some special properties, and we will discuss right now about these properties. Do you understand? Right. So with this broad overview about the colloids, let me get into the further topics. We'll be discussing now the classification of colloids. Okay. We discuss about the colloid where it contains two parts, that is dispersed phase and dispersion medium. So this colloid can be classified based on these two. Okay. One is, that is classification based on the physical state of the dispersed phase and dispersion medium. So classification based on physical state. Okay, so based on these physical states, we can classify colloid. Secondly, the nature of interaction, between dispersed phase and dispersion medium. So we can classify based on the interaction between dispersed phase and dispersion medium. Okay. And third, this can further be classified based on the particles of the dispersed phase. So the particles of the dispersed phase only. Okay. So how I have classified now, can you repeat it? The colloids can be classified based on the physical state of dispersed phase and dispersion medium. And it can also be classified based on the interaction between dispersed phase and dispersion medium. Then this is also classified based on the particles of the dispersed phase. So what I have done is a concept map. So in your book, it would have been given as line after lines. So better you can map it properly and link it. You will get a beautiful icon for that concept. So always practice this kind of concept mapping. Okay. So it improves your memory also. Let me proceed with the classification based on the physical state of dispersed phase and dispersion medium. That is the first one. Okay, right. Now let me discuss the first one, classification of colloids based on the first aspect. Okay, so now we have once again the dispersed phase and dispersed media. Okay, right. Now when the dispersed phase is solid, okay, when the dispersed phase is solid, and the dispersion medium is also solid, then it is called solid sol. Okay, what do you call it? Solid sol. This is one type. Okay, so examples are glass, colored glass, they are of this type. Note down, colored glass. Then gemstones. So they are of, both of them are solid. In this case, dispersed phase is also solid, then dispersion medium is also solid. So that is why it's called solid sol. Okay, this is type 1. Now, type 2. Type 2 is solid liquid. Okay, the next one is solid liquid. Type 2. This is solid and this is liquid. This is called sol. That's all. Simply say sol. Okay. And then you have solid gas, and that is called aerosol. Solid gas. This is known as third type, aerosol. Then you have the next type, that is solid aerosol. Means that is, you can have some example like smoke is an aerosol, dust. Okay, so smoke and dust, smoke and dust. And for this sol, paint and some cell fluids. Okay, for this one, paint and cell fluids, cell sap or cell fluids. Okay, right. And the next one is solid, liquid solid, that is called gel. Okay, liquid solid, liquid and solid, that is called, here the dispersion medium is solid. It means the major portion is solid where liquids are spread. So this is called the fourth type, that is gel. Okay, gel. Ink, gel pen, all these things, So this is very simple. Cheese, you can say cheese, butter, jellies, etc. Okay. Then you have liquid emulsion. So this liquid is called emulsion. This is liquid. This is also liquid. Then this is known as emulsion. Everyone has unique name. Okay, please understand that. Emulsion, emulsion paints, is it not? Then you have milk. Milk is also very good emulsion. Hair cream. Okay, so these are all emulsion. Then liquid gas, that is known as liquid gas. That is also called aerosol. Sixth type, aerosol. Okay. So under aerosol, you have that is a fog, mist, cloud. So insecticide sprays. So these are all coming under this aerosol category. Then you have gas solid, that is called again solid sol. That is gas solid. You have gas solid. This is also solid sol, seventh type. Gas solid sol. Write down as solid sol, seventh type. Solid sol. Understand? Solid, sol. Then we have liquid, liquid. Solid sol, the best example is gas solid sol. Pumice stone, that is, it is useful for cleaning your, that is a palm, then legs, okay. Then foam rubber, that is also solid sol. Foam rubber is also solid sol. Then we have gas liquid, that is the frothing, is it not? So foam, it's called foam. Gas liquid, that is the eighth type, that is foam. Okay. So, example, whipped cream, shaving cream, soap lathers, frothing. So these are all called foaming. So see, based on the physical state of dispersion medium and dispersion phase and dispersion medium, we have classified the colloids into 8 types. What are those? If the dp, that is the dispersed phase, is solid, and dm, dispersion medium, is solid, then it is called solid sol number 1. Then the next one sol, the next one aerosol, gel, emulsion, aerosol again. But this is based on liquid gas. And then you have solid sol, that is gas and solid sol. Then you have foam. So likewise, you have 8 types of classification of colloids. Do you understand this? Let us proceed with the classification based on nature of interaction between the dispersed phase and dispersion medium. So this classification is based on the nature of interaction between the dispersed phase and the dispersion medium. So this colloid, once again, it can be classified as 2 in this case. Previously we discussed 8 types. Here it is 2 types. That is lyophobic, L-Y-O, lyophobic, and another one is lyophilic, lyophilic. Lyophobic means, that is, lyo means solvent. Lyophobic, you can say lyophobic and lyophilic. Phobia means hate. So solvent hating. So this is solvent hating. So this type of colloid, okay, they hate solvent. They are not agreeable so easily with the dispersion medium. Whereas this type of, that is lyophilic, that is solvent loving, you can say. So that is easily compatible. Okay, so solvent loving. The same lyophobic and lyophilic can be called hydrophilic and hydrophobic when water is used as the dispersion medium. You please remember, when water is used, then it is known as hydrophilic and hydrophobic. Hydro means water. So when I say lyophobic, lyophilic means any solvent. So solvent, particularly non-polar solvent here. So solvent hating, this is solvent loving. Okay, this is point number 1. The next point in this case, see, the lyophobic do not form immediately colloidal sol. Do not form. They do not form immediately colloidal sol. They don't form naturally colloidal sol. That is colloidal particle dispersed in dispersion medium. It needs some sophisticated methods. We'll be discussing in detail about that. Whereas here it is easily formed. Easily formed colloid sol. Okay. And the next point is this does not form, for instance, that is, we have got some colloidal particles like any gum or gelatin. When it is dissolved in a particular solvent, they disperse readily because they are lyophilic. But when we evaporate, we can get back once again this sol, and that is why this is a reversible sol. Are you able to understand this? Reversible sol. Whereas once it is dispersed, and as I already mentioned, it needs sophisticated tool also. So this is irreversible, otherwise it becomes irreversible sol. Irreversible sol. So it needs some special technique, special method to make colloidal sol. Which one? Lyophobic. So needs special technique, special method to form sol, colloidal sol, whereas it doesn't require. No need to form sol. Here, this is not stable, not stable. Okay, it does not give stable sol. Just by adding sodium chloride, it will come out. It precipitates, okay, it precipitates immediately. Whereas here, it is stable. You can once again remix with the same solvent and get back. Okay, that's why it's called reversible. Are you able to follow? Okay, so these are irreversible sol, whereas this is reversible sol. You understand? And so, since at any time it can break, it needs some stabilizing agent to make uniform and more stable. So, it needs stabilizing agents, whereas this require no such stabilizing agent. No stabilizing agent. You understand this? So this is the second method of classification. Let us see that this classification based on type of particles of the dispersed phase. So based on the type of particles of the dispersed phase, we can classify the colloids into three major types. Let me write quite once again the classification now. It is the third type of classification. This colloid is classified into three. One is multimolecular colloid. Multimolecular. Another is macromolecular. Macromolecular. Molecular. The third one is miscellaneous. MICELLES. Miscellaneous. It can also be called associated colloids. Okay. So we have type A, what is that? Macromolecular. Type B, type A multimolecular, type B macromolecular, type C miscellaneous, that is associated colloids. Let us discuss the first one. Multimolecular means they are in large numbers, and size is smaller. So smaller size. Okay. And the diameter of colloid may range less than 1 nanometer. Then they form uh, different different types of sizes also in the same thing, but it will be smaller. It may have a range. Example, we can have gold sol, gold sol. Then we can have sulfur sol, okay, sulfur sol. So they come under this category, multimolecular. Okay, they are multimolecular. They have large number of atoms with a smaller size. They aggregate together to form a special type. Okay, right. Then under macromolecular, the size is bigger. Okay. Comparatively, when I say size is bigger, means I don't compare with the suspension. Among these, the size is bigger. Then they are quite stable. They are quite stable. Then they resemble almost true solutions. They appears like true solution. True solution. Okay. And the best examples are starch, cellulose, proteins, enzymes. So we can have all this. Even enzymes you can include. Then the specialty of this one, it can be synthetically made also, man-made macromolecules or macromolecular colloids or polythene. These are all synthetic. Polythene, nylon, some polymers, okay? Synthetic rubber, etc. And regarding associated colloids, they are substances which at low concentrations behave as normal strong electrolytes. So at low concentration, okay, they behave like strong electrolyte. Strong electrolyte. Strong electrolyte means was that is like NaCl solution or HCl solution or NaOH solution. Okay. So at lower concentration, but at higher concentration, okay, they form aggregation. That is, they exhibit colloidal nature at higher concentration. So at higher concentration, they form aggregated molecules called micelles. You understand? Okay, right. So the formation of such micelles, it can take place only at certain temperature. That temperature is called TK. Take down TK. It's called Kraft temperature. Kraft temperature. So what is Kraft temperature? The temperature at which micelles are formed. So they are formed at this temperature. That's why it's called Kraft temperature. Okay, and the concentration, required concentration to form such micelle, that is called the critical micelle concentration. Okay, CMC. You can note down here. CMC. What is that? That is critical micelle or micelle concentration. So that is the concentration required to form micelle. This is called critical micelle concentration. Okay, and the next one is on dilution. On dilution, then colloids revert back. The colloids revert back to, that is, ions, individual ions. Individual ions. Okay. So, example, we can say the surface active agents like soap, detergent, these are all capable of forming such type of micelle. Soap, detergent, etc. Okay. So, in fact, they have both lyophobic and lyophilic. Lyophobic and lyophilic colloids. Okay. So they have both parts. And in fact, its size, the CMC size is around, CMC concentration is around 10 power minus 6 to 10 power minus 3 mole per liter. That is the critical concentration, micelle concentration. Okay, mole per liter. Do you understand? So after this, we will discuss the mechanism of formation of micelle. Okay. Let us discuss about the micelle formation or the mechanism behind the formation of micelle. Before that, you should know something about soap. Soap is the sodium or potassium salt of long chain fatty acid. Long chain fatty acid. You know something about formic acid. What is the formula for formic acid? HCOOH. Acetic acid, CH3COOH. So likewise, you can elongate the carbon chain. So with the increase of length of carbon chain, the non-polar nature increases. But at the same time, in the COOH, in the carboxylic acid function group, when you replace hydrogen by sodium or potassium ion, that becomes polar head. So let us consider stearic acid. It is C17H35 COOH. Now what is the salt? The sodium salt of stearic acid, which is nothing but sodium stearate. So Gokul has clearly illustrated this diagram with a long chain of stearate unit, that is C17H35 COO minus. So he has done it very patiently, but we have to check whether it contains 17 carbon atom, that is 16 carbon atom plus that C. Okay, right, COOH, C of COOH. So this is the long tail and this is the hydrophobic tail. Do you understand why? Because hydrophobic means, hydro means water. So water hating. So this part is the water hating part. The other one is hydrophilic head. That is the COONA portion. That is the salt portion, the salt formation portion. That is the ionized portion. See, let us consider a dirt. Generally, dirt is a non-polar greasy item, oily item, waste, anything. So we need to clean that. So with the help of water alone, we cannot clean 100%. So that is why during this lockdown period, because of the attack of corona, we have been advised to clean the hands at least for 20 seconds. Do you know why? Because this soap is capable of breaking the protein. So it will kill the germ. And not only that, in fact, since it has the longest chain of hydrocarbon unit, it is compatible with non-polar item like oil or dirt. At the same time, the polar head is miscible with water. So it makes an understanding between oil and water, or non-polar and non-polar dust or grease and water, and thereby it forms a it forms a micelle, a spherical structure with such kind of long tail and polar head. Let me show you another structure. This illustrates the cleaning action. It's called the cleansing action of the soap. So in a cloth, there is a spot of dust or grease. Now with that, you know very well, grease is a non-polar item. So with the help of this non-polar tail, we are able to penetrate these grease particles and make it dispersed. Okay. So that, and the polar head, that will be miscible with water. So instantly the grease droplets are surrounded by the stearate ions and thereby the micelle is formed. Okay, so that it can be easily cleaned. Okay, right. So thank you for watching this video, and we will continue the next part of this colloidal chemistry tomorrow. Thank you very much. So please go through whatever we have discussed. Try to develop always some concept mapping. Okay. All the best, guys. Thank you. Good night.